In this final video, we'll go through some query optimization techniques. When it comes to query optimization, there's not a lot of simple, if this, then do that type advice. Because if it were that simple, the query planner would just do it. Remember that the query planner has had a lot of time and research put into it, with the explicit goal of finding you the lowest cost plan for any query that you provide. And additionally, whether you get a better plan depends heavily on the data itself. For example, even when you have an index, the better approach can sometimes be a sequential scan if you're reading a large number of rows from the table. And that's what makes optimization such a tricky thing to talk about. It's the combination of both the query and the data that impact the type of query that will work best in any given situation. So like most problems in optimization, the best approach is generally first to write your SQL for readability. Write your query in the simplest possible way that makes sense, and then optimize second if your performance is not where you want it to be. So the first thing you can do is evaluate different ways that you can write the same query. Completing the exercises in this course so far, you would have noticed that many queries can be written in several different ways. Sometimes for the exact same results, you could use joins, subqueries, set operators, Windows functions, and more. If you've written a query and you're not happy with its performance, consider and evaluate the different ways that you could have written that same query. And in general, you want to avoid overusing subqueries and try to leverage joins wherever possible. They generally allow for better optimization opportunities. You might remember as you're working through this course, you encountered an exercise several times where you had to identify missing rental IDs. Let me show you an example now of something analogous but working with the test messages table that we created in a previous video. So if you recall, in a previous video, we created a messages table, and that messages table had 1 million rows. The IDs were numbered sequentially from 1 to 1 million. What I'm going to start out doing is just deleting 6 of the rows from that table. And now I want to show you 3 different queries which will allow you to return those missing IDs. So this is analogous to the missing rental IDs exercises that you completed throughout this course, but now we're just working with the messages table, which has much more data. The first approach is to use a correlated subquery. Let me just run the query by itself to show you the results. So those are our missing rental IDs, so the query itself is correct. This approach uses a correlated subquery. It first calls generate series, and generate series is used to generate a sequence from the min to the max, so from 1 to 1 million, and then it filters those rows using where not exists, and it uses a correlated subquery to test for the existence of that ID in the messages table. Running this in full with explain analyze, the total cost comes to about 6,500, and the execution time is about 1 second. A second way you could achieve the same result would be to use a common table expression and a window function. This query returns exactly the same results as the previous query. The formatting is slightly different, but the end result is identical. And now let's look at the query plan for this. You can see that the execution time was quicker, around 500 milliseconds. So this approach was faster than using the correlated subquery. Finally, a third way that you could accomplish the same thing is using set operators. Let's just run the query itself again. You can see that you get the right output. And now running with explain analyze. And the runtime of this is around 700 milliseconds. So for this instance, the fastest approach was the CTE with the window function, the second fastest approach was using the set operator, and the third fastest approach was using the correlated subquery. So always bear in mind that you have several different ways that you can approach the same problem. The second tip I want to share is to look for missing indexes. I would say that missing indexes are probably the leading cause of query performance issues. Adding the right indexes can cause an order of magnitude or several order of magnitude performance gains. To identify missing indexes, look for sequential scans happening on large tables, and also you might want to evaluate different types of indexes. In this course so far, all we had time for was to look at using the default B-tree index, but there are several other index types that you may want to consider. A third technique for improving the performance of your queries is using partial indexes. Partial indexes let you index a subset of the records in a table based on a given condition. So you don't index an entire table, you just index some smaller subset. And of course then, the resulting index is much smaller and it's much faster to work with. So as in the example here, you could create an index on the customer table on the email column here, and you specify a where condition, so where active equals 1. If you're commonly querying the customer table for that email column, and you often include that condition where active is 1, then the index will get leveraged and your query will be faster. A fourth performance optimization tip is to be aware of CTEs and how they can act as what's called an optimization fence. This is true in PostgreSQL 11, which is the latest version at the time of recording, and below. When I say optimization fence, what I'm talking about here is the query inside the CTE actually gets evaluated and materialized independently of the main query. Sometimes your main query may have additional conditions or joins or other things that are happening which should present optimization opportunities, but don't because the CTE is evaluated independently like it's a black box. This has now been fixed in Postgres 12, which is due to come out shortly, but if you're working with PostgreSQL 11 or below, be aware of this. You may find that you can get some performance benefit if you discard a CTE and just inline it in the main query. A couple of other query performance tips, and I'll jump over to some code and give some examples for each of these. Generally, you want to see if you can get away from using in or not in. Let me jump over to some code and show you what I'm talking about. In this course, one of the exercises that we worked through was to return all the customers that have rented films. Here's a version of that query that uses in and a subquery. So it selects all the customers from the customer table, and it looks for the customer ID being in the rental table. That's one way to write that query. Another way you could write the same query would be to turn that into an inner join. So you join the customer table using the customer ID column onto the rental table. And by doing this, the join condition itself will take care of filtering out any customers that don't appear in the rental table. This query will return the same results, and generally you'll find that this query, this version using an inner join, will perform faster than this query, which uses a subquery and in. So if you're having performance issues with a query that uses in, see if you can instead turn that into a join. Also, you may want to look for queries that are using not in and look for whether you can use either not exists or use a left join instead. So here's a query that returns the films that don't have any actors. So it selects all the films from the film table and it says where the film ID is not in the film actor table. An alternative way you could write the same query would be to use where not exists. So again, it starts the same from film where not exists, and then it uses a correlated subquery to look into the film actor table to see if any of the film IDs match the outer query film ID. So that's a correlated subquery. Because we're using where not exists, we can just select any columns, it doesn't matter. All it's checking for is on a film by film basis, the existence of any films with the same ID in the film actor table. Generally, using where exists will perform better than using not in. And a third way that you could even write the same query is to use a left join. You can left join from the film table onto the film actor table and then filter the results for where the film ID is null. Typically, you'll find that this third way is even faster than using not in or not exists. A third query rewriting tip is to use filter instead of case expressions. So for example, if you're performing an aggregation, so you're using sum or count, and you want to count based on some sort of condition, if you're writing ANSI SQL, you have to write that as a case expression, but with Postgres, you can make use of filter, and you might find that that gives you some better performance. Finally, as I've mentioned a few times now, try to avoid overusing subqueries. Most people who start out writing SQL tend to overuse subqueries quite a lot, but as you begin to think more in terms of tables and sets and joins, you can often find that you can move away from subqueries and use window functions, set operators, or joins to accomplish the same thing, and it will generally be faster. Query performance and optimization is overall a very deep and complex topic, and it's a moving target as well, because as new versions of Postgres and other database management systems are released, they make constant improvements to the behavior of the query planner. So as I mentioned earlier, just start off writing your queries in the most simple way possible, then look for indexes that could be missing, and then only after you've done those two things, start to delve into different ways that you could rewrite queries or look for other performance gains.